What specific problem does your proposed ensemble-based method aim to solve in the context of superalignment, and how does it address the limitations of previous approaches relying on a single weak supervisor?
Our proposed ensemble-based method aims to solve the problem of weak to strong W2S generalization in the context of superalignment, specifically addressing the limitations of previous approaches that rely on a single weak supervisor. These prior methods often suffer from a lack of diversity and robustness in supervision, as a single model's perspective can be insufficient for instructing stronger models on complex tasks. By employing an ensemble of multiple weak models, our method enhances the supervisory system, allowing for a more comprehensive and effective guidance for stronger models. Additionally, our approach incorporates a novel AdaBoost-inspired mechanism that not only improves the knowledge transfer from weak to strong models, but also refines the weak models themselves, ensuring they are better optimized for complex problem settings. This ensemble strategy ultimately leads to significant performance improvements, as demonstrated by our experiments, where the combined weak models outperform single weak supervisors and enable stronger models to achieve results comparable to those trained on high-quality data.
How does the proposed method or algorithm work? Please illustrate step by step, particularly detailing the easy-to-hard framework and the AdaBoost-inspired ensemble approach.
The proposed method operates through a structured easy-to-hard E2H framework combined with an AdaBoost-inspired ensemble approach. First, weak models are trained on easy data, which consists of simpler tasks that have labeled solutions, while stronger models are trained on hard data, which lacks sufficient ground truth labels. The weak models then generate pseudo-labels for the hard data, effectively supervising the stronger models. The AdaBoost-inspired ensemble method aggregates the outputs of multiple weak models, utilizing a weighted majority voting mechanism to create a consensus answer for each hard question, thereby enhancing the robustness of the supervision. This ensemble approach not only improves the weak model's generalization capabilities, but also allows the stronger models to achieve performance levels comparable to those trained on high-quality data, demonstrating the effectiveness of the W2S generalization process.
Can you walk me through a simple yet illustrative example that demonstrates the inner workings of your EnsemW2S AdaBoost algorithm? How would it process an easy question to help a stronger model tackle a more complex task?
The EnsemW2S AdaBoost algorithm operates by leveraging multiple weak models, each trained on simpler, easy tasks, to generate pseudo-labels for more complex, hard questions. For instance, consider a scenario where weak models are trained on basic math problems, easy questions. When faced with a complex math problem, hard question, each weak model generates its answer based on its training. The algorithm then employs a weighted majority voting mechanism, where the outputs of these weak models are aggregated to form a consensus answer. This consensus acts as a pseudo-label for the hard question, which is then used to train a stronger model. By combining the diverse perspectives of the weak models, the EnsemW2S AdaBoost algorithm enhances the supervisory signal, enabling the stronger model to learn effectively from the generated pseudo-labels, ultimately improving its performance on complex tasks.
What are the theoretical or practical benefits of using your method as opposed to existing alternatives? Can you quantify improvements in efficiency or accuracy based on your experimental results?
The theoretical benefits of our method, EnsemW2S AdaBoost, lie in its ability to combine multiple weak models to provide stronger supervision, addressing the limitations of relying on a single weak supervisor. Practically, this ensemble approach enhances the generalization capabilities of weak models, allowing them to effectively guide stronger models in complex tasks. Our experiments demonstrate quantifiable improvements, with accuracy enhancements of up to 14% over baselines in binary classification tasks, and an average improvement of 7% across all model pairs. Additionally, in supervised fine-tuning tasks, our strong model trained using weak labels outperformed the strong model trained on ground truth in several instances, showcasing the effectiveness of our method. Overall, our approach not only improves weak model performance, but also enables stronger models to achieve results comparable to those trained on high-quality data, thus significantly advancing weak-to-strong generalization.
How did you validate or test the effectiveness of your method? Describe the experimental design, the datasets employed, and the benchmarks used to demonstrate the performance of your new approach.
To validate the effectiveness of our method, we conducted experiments using two different strategies. One involved random training data splits, while the other utilized an easy-hard data split. We employed the SciQ dataset for binary classification tasks and the ARC and Quartz datasets for supervised fine-tuning tasks, converting them into binary labels and generating multiple-choice pseudo-labels, respectively. Our experimental design included training weak models on easy data and strong models on hard data, with the performance gap recovery, PGR, as a key metric to assess the weak-to-strong W2S generalization. We compared our Ensemble method, EnsemW2S AdaBoost, against a baseline of single weak models, observing improvements of up to 14% in accuracy and significant PGR values, indicating that our approach effectively enhances weak model supervision for stronger models. Additionally, we performed ablation studies and token-wise comparisons to further substantiate the robustness of our method across various model pairs and datasets.
What limitations or drawbacks does your method have, particularly concerning resource intensity or generalizability to other tasks? Are there specific scenarios where it may not perform as expected?
Our method, while effective in improving weak-to-strong W2S generalization, has notable limitations regarding resource intensity and generalizability. The Ensemble approach, particularly the EnsemW2S AdaBoost algorithm, requires significant computational resources due to the need to train multiple weak models and aggregate their outputs, which can be resource-intensive, especially for large datasets or complex tasks. Additionally, the method's performance may not be consistent across all tasks. For instance, we observed that smaller models benefit more from ensemble learning, while larger models may not show significant improvements due to their tendency to learn all available information, limiting the diversity needed for effective ensemble training. Furthermore, the complexity of the easy-to-hard E2H generalization problem may hinder performance in scenarios where the disparity between easy and hard tasks is minimal, as seen in the ARC dataset, where improvements were less pronounced. Thus, while our method shows promise, its effectiveness may vary based on model size, task complexity, and available computational resources.